Heap is just nothing, is a special case of binary tree. So what are the properties of a binary tree? Then we'll move to heap, right? So in binary tree, we will have one root and all the descendants nodes are the childs of the root nodes. Maybe transitively they are child. So and each node will have at most two childs, as we know in binary tree. And you can see we have another properties levels. You can see all the vertices falling at level 0. That will be only the root. Will have only one vertex at root levels, and at one levels we will have two vertices, because how do we actually find the number of vertices? 2 power level number. So at level 2 you can see 2 power 2 vertices are there, and the last levels may have at most 2 power 3, right? These are the properties, and one more properties we have, height. And height is what? The number of elements, or the number of vertices when we want to visit the leaf from the roots. That would be the height. You can see from root, if we want to go 1, so we will go 1 2 3, so that is the height is 3. You can see over here. And the vertices, vertex of the vertex at the leaf nodes with height of that node is 0, because and you can see height of this one, it will becomes 1, and you can see 2, all the vertices falling at these levels 3. This is how we compute the height. The order of increment of height is from bottom to up, and level of increment of levels be always be from root to leaf nodes, right? This is one things. And another thing, so how do we actually we identify this as a heap? This is a crucial thing you should know about. In heap, we actually fill the element from left to right. You can see over it. First we fill 16, then 14 and 10 would be the child of. Then next elements, if you want to fill in heap, that it will come here, here, then from left to right we fill the labels. Level wise we do filling, right? If any labels which is incomplete, that will be on the last level of the binary tree, if the binary tree is a heap, right? This is how we actually design a heap, and what is the property of heap. Another things, if we want to find out the number of elements at any levels in terms of height, and what we will have, we have a formula. We can take seal of n is what? Number of elements by 2 power h plus 1, right? So this is the sometimes we get odd numbers, then we consider as a odd plus 1, that becomes a even, that would becomes the number of element at any level. So you can verify yourself. You take numbers, the number of number of vertices in this heap by 2 power h plus 1. H plus 1 was, if we talk about this one, h will become 1, right? In this way we can find out number of elements at any levels, right? And one more things, in balance tree, you can see this is the balance tree. Why this is balance tree? If we take two subtrees, and what we find that of this root we have two subtrees, and take difference of these two subtrees, we see this is at most 1, so that's why this is balance tree. And we know in balance trees, height of balance tree is always log n. So that is the reason I have written over here h is equal to log n, right? So these are the property I have written. You can read yourself, and we will move forward and see the two type of heap we have. First one is a max heap, and the next one is a min heap. When you are required, you are asked frequently to find out the minimum element of the array, or from binary tree or from heap, then in that case you will use min heap. If you are asked frequently the min max element from the array, then you use the max heap, right? So what is the properties of heap? Parent would be greater than or equal to of both child 1 and child 2. And in min heap, in parent will be the less than or equal to of both child 1 and child 2. As we know, we have at most two child. Now we will look at that how do you actually, why is this binary heap or heap is so popular, right? So the popularity behind binary heap is storing. We can store this binary heap or this heap very easily in array, one array. So how do we actually store? We have you can see this is the same binary tree I have copied from here, and I just have written some numbers over here: 1 2 3 4 5. These are the numbers I have written. These numbers are nothing, these are the index of it. You can see we have an array, and this is what location means index I have written, and these are the value at that index, right? Particular index. So you can see the any numbers which is written over here, these are not overlapping to each other, so that's the any value will any value which is present in this tree will fall only one place. So because one-to-one mapping is there, one is mapped with this one, two is mapped with this one, three is mapped with this. So that's why the values will not overlap to the same locations, two values, right? Now can we have any formulas for that? How do we actually find the child of any parents, or parent of any child? So do you have do you observe any relations between these two numbers? You can see left child of any parents, you can see the location of left child of any parent is just double of the location of parent. You can see over here, for the location of left child is 10 of this 5. So any numbers, if you take 10, the parent location is 3 and child location is 6. What about next right child? Right child location is always be 6 plus 1, right? Plus 1 of location of left child. You can see 4 plus 1 5 and 8 plus 1. This is how we actually store these binary heap into the array. I hope this is clear. Now, this is the same thing I have written over. If location of parent node is I, then the child left child location will be 2i, and next right child will be 2i plus 1. This is how we actually find out the location of either left child's, right child's, or parent. But what if you are given the location of child, can you find out the location of parent? Yes, you can do it. Suppose the you are given index of 7, you are asked to find out the location of parent. In that case, what you do, simply take a half of these numbers and take seal, because 7, if you divide by 7 by 2, what you get numbers, you get 3.5, right? So seal value would becomes 3, right? So minimum integers, or the lowest integers of 3.5 would be 3. So that is the reason location would come 3. Now what are advantage and disadvantage of this Max-Heap or min-heap? If you are asked frequently to find out the min element from the min-heap, then you can do it in order of 1, because the min elements will be at the top of any root, any binary tree. I means it always be a root of a binary tree. Right. What about max elements? If you are having Max-Heap, in that case the max elements will be at the top of binary. It other in other words, it will be the root of the Max-Heap. Right. In this way, we can find out max or min elements from the heap very easily. At a times, only one we can get in order of 1. Suppose if we have if we have suppose if we have a Max-Heap, you can get my max element in order of 1. If you have min-heap, and you can get my min element from the heap in order of. So if you have max, if you wanted to find out the many elements, you cannot get in order of one. So if you have only min heap, then you can get minimum element in order of one. I hope this is clear. So disadvantage of this binary heap is what? Insertion and deletions of any element in this heap takes log in time complexity. I hope this is clear. Now we will move forward and design a max heap. And we will look at here how do we actually design the max heap from the given array, right? Suppose you are given this array, and array having these many elements, and we start making the by Max-Heap, right? So we will take first element 4. You can see 4 will come here, and next element, as we know, we fill from left to right, yeah, and then the 1 will becomes the left child of 4, and the 3 would comes, you can see 3 will come here, and in the same times we compare the parents would be greater than or equal to of both child. So that's these properties is still hold, so that's why no swapping will take place. Then let's add another elements, that would be 2, and we have added, as we know, we will fill elements from left to right. So no, 2 will come here, so you can see or 2 here came here, and we compare again with its parents. If it is holding the property of Max-Heap property is parent must be greater than or equal to of both childs. You can see the child of 1 is 2, and it is violating the condition of Max-Heap. Max-Heap condition is what? The 1 must be greater than or equal to 2. So it is not holding, so that's why we do swapping. And if we do swapping, then 2 will come here and 1 goes to here. So again we will check this value has been changed, so that's why we have to check it again with the parent of this one. And if it is holding, then we don't do anything, otherwise we will do swapping, right? And if in the next lesson we will add another numbers, 16, you can see if we do it, and we check the Max-Heap property. What Max-Heap property is? We compare 16 with its parent from 2, and what we see here, the parent is not greater than of 16, so that's why it violate the condition of Max-Heap. So that's why we do swapping, right? What we see 16 will come here. Now you see the child of 4, which is 16. As we know, max parent node must be greater than or equal to of child, so that's why this condition is not holding here, so that's why we do swapping. Then 16 had come here. What you have observed here, if this is a Max-Heap, then the maximum elements always be at the root levels. So you can see all the elements which are present here, these are the less than or equal to of this max root element. So we repeat the same process for 9, 10, 14, 8 and 7. What we get the resultant binary heap, right? So you can do all those things. You can write algorithms very easily, but in I will cover the algorithm in the next lecture. Thank you for watching. So if you feel this lecture is helpful for you to understand the binary heap, then you can share with your friend. Thank you for watching this video.